Hi, this is Ms. Spazen, and today we're going to talk about general properties of solutions, which is section 4.1. So let's start by first defining what a solution is. So a solution is defined as a homogeneous mixture of two or more substances. So when we say homogeneous, that means that it's evenly mixed, so you can't see the components that make it up. And because it is a mixture, it could be separated by physical means. Now usually when we think of solutions, we think of liquids, but solutions can also be made out of gases, and they can also be made out of solids. So when we make a solution, there are two parts to it. There's a solute and a solvent. The solute is the substance that's present in a smaller amount, so it's what's being dissolved. The solvent is what we're dissolving the substance in, or the solute in, or it's the substance present in greatest abundance. Now usually when we think of a solvent, we think of water. So when you have water as your solvent, those are called aqueous solutions. But you can have other things as solvents also. There's a lot of substances that dissolve better in solvents like alcohol or other types of acids. But most of the solutions that we're going to talk about at this particular level are aqueous solutions. Another way we can classify solutions is we can describe whether or not they are electrolytes. So an electrolyte is something that has ions in solution. So if you dissolve certain substances in water, they form ions, and because they form ions and they are classified as electrolytes, that means they can conduct electricity. If you have something that doesn't form ions in solution, those are classified as non-electrolytes, and those don't conduct electricity in solution. So we're going to look at a little more detail about what we mean. So one example of an electrolyte is an ionic compound. So if you have an ionic compound, you have a substance that when it dissolves in water, the ions dissociate. So what that means is if you have a substance like NaCl, in solution, this becomes Na plus and Cl minus. So in this particular picture here, here's our Na pluses, and then here's our Cl minuses. And this big block here is the salt crystal that's starting to dissolve and starting to dissociate. This particular salt substance is dissolved in water, so you probably recognize these other little molecules as water. So if you remember what the structure of water looks like, you've got H2O, and H2O, or water, is a polar molecule. So what that means is part of this molecule has a partial positive charge, which would be the H's in this case, and the other part has a partial negative charge. So those little signs are lowercase deltas, and delta plus means partial positive, delta minus means partial negative. So when the salt dissolves, or when it dissociates, if you look a little closer at what's going on over here with the positive one, notice that the oxygen, which are the red molecules or the red atoms, are surrounding that sodium ion. So the negative side of the water molecule is surrounding the positive ion. And if you look at this one over here, the positive part of water is surrounding the negative ion from the sodium chloride. So that's one of the reasons that water is such a good solvent, is because it does have a positive piece and a negative piece, so it makes it a great solvent for ionic compounds, because when ionic compounds dissociate, you get a positive and a negative. If you have a molecular compound in water, you don't get ions formed in solution. So these particular substances do not conduct electricity. So again, if we look at our little sample here, here's our molecular compounds that are in there, and notice those do not dissociate. So those stay completely combined together. So they don't break apart into ions. If they don't break apart into ions, then they won't conduct electricity. Now there are some exceptions here for molecular compounds, and we'll talk more about these in a couple minutes, but acids and weak bases will actually dissociate in water, but the rest of the molecular compounds that we talked about won't. Okay, another description you can look at to be a little even more descriptive is whether it's a strong or a weak electrolyte. So if you have a strong electrolyte, this is something that completely dissociates in water. And when we represent this, we show an arrow in one direction. So for example, if we look at something like sodium chloride, which we were just talking about a minute ago. So I have NaCl. NaCl in solution completely dissociates. So I get Na plus and I get Cl minus. So my arrow is only going in one direction, and that is a strong electrolyte, and you can tell if you take a bulb and put it into put the electrodes into the solution, so this would be like a solution of sodium chloride here, you get a nice bright, brightly lit bulb. And we'll do some examples with this in class tomorrow so you can see some of this. Another example of a strong electrolyte is hydrochloric acid. So this is that exception, that molecular compound that is actually an electrolyte also. So that completely dissociates into H plus and Cl minus. Now, weak electrolytes only partially dissociate in water. So when we show these dissociating, we use a double arrow. So an example here, and I realize this is the same picture, but these do not, the light bulb would not be as bright. So an example of a weak electrolyte would be acetic acid. So HC2H3O2. So acetic acid is a weak acid, so a weak acid is also a weak electrolyte. So when we showed the dissociation here, we show a double arrow. So what happens here is you have some dissociation, but then you also have some of the undissociated acid in that solution as well. As a result, you only have, or your light bulb is not as bright. Strong electrolytes are strong acids, strong bases, and then they're also the soluble ionic salts. So soluble ionic salts are just ionic compounds. And then the strong acids, there are 7 strong acids that are listed here. And then strong bases, which classify strong bases as group 1 metal hydroxides. So lithium hydroxide, sodium hydroxide, potassium hydroxide, etc. So any hydroxide combined with a group 1 metal or an alkali metal, and then the heavy group 2 metal hydroxides. So starting with calcium down, calcium hydroxide, strontium hydroxide, and barium hydroxide, all the way to the bottom. So those are considered your heavy group 2 metal hydroxides. Our weak electrolytes are weak acids, like we saw a minute ago, and weak bases. And we'll talk a little more about the weak acids and the weak bases in the next couple sections.